Okay. To understand these kind of deformations, it is important to get some basic understanding of mechanics. The deformation is typically something that happens or is analyzed or is understood within the field of mechanics. And mechanics is all about stress, strain, and material properties. And to demonstrate that, I brought you an Aachener Pinten. Aachen is quite famous for these Pinten. And maybe we can put a little video of this at close-up. This cookie is quite hard. You can actually hear it, okay? But what is so interesting is that if you load it by pushing down your fingers very gently, then you feel that the cookie is bending. And not what you expect. It should maybe be breaking. It is actually bending. And over time, and with a little bit of patience, I've actually made a fold. I bent it. I made an anticline. Okay? Now, from a piece of glass, I could not have done that. So, stress, it's the forces that I use to bend the cookie. Strain is the displacements, is the movements. And the material properties, that is what the cookie actually has for herself, or for itself. And this is a very interesting material, the Aachener Pinten, because if you bend it over sufficient large curvatures, then it will break. Okay? So in the beginning it is ductile, and we will learn this term, and then later it becomes brittle. Okay? So it shows a behavior which is really quite complicated, and it is somewhere in between the folding and the folding. And I would give you the homework for this lecture is go home and try to do this experiment and really feel that if you push hard and quickly, then the cookie will break. But if you push just very gently and wait, then it will flow. It will be ductile. And last year the homework was to make a movie or a little report or a photograph of a nice experiment where you demonstrate that you've understood this concept. And last year I've had some very, very interesting ideas and little movies. People put it in the fridge and in the freezer and all kinds of games that they played with it. So please surprise me. Okay, after the lecture you can try. Of course, if you are a structural geologist or a tectonician, you want to also make money. You want to have a good career. And structural geologists are used or are employed in many, many different parts of the industry. Exploration and mining of ore bodies, metallic ores, salt, it's almost always connected in some ways with structures, with folding, with faults. Structural geologists are hired and are kept in high regard in these parts of the industry. Engineering geology, the building of tunnels, it's very important to understand the structures which are present in the earth to prevent collapse, to prevent disasters. Of course, we are quite closely related to neotectonics. My colleague Klaus Reicherter is teaching you that subject. Then exploration and mining of oil and gas. Structural geologists and people who work in tectonics are employed in large amounts. Most of our PhD students and MSc or MSc students who are finishing, they are getting jobs with the oil industry at the moment. But of course, there is a lot of work for academicians, people who work in universities or in geological surveys, and do tectonic analysis. Here is just a beautiful picture from Greenland. I don't know how well you can see it, but here is a huge fold, a syncline in a gneiss in Greenland, and the rock face is 500 meters high. To really be able to appreciate the structures, you often have to go a little bit further than just the Eiffel Mountains here, because the places where there is a good outcrop That's where you see the really fantastic structures. Okay, so this was a kind of an introduction, homogeneous, heterogeneous, isotropic, where you can find a job, what it is all about with the materials. And now let's talk a little bit about models. Oops, I made a mistake. Okay, so there is more work for structural geologists in the exploration and production of oil and gas, the analysis of seismic hazard, fluid flow, hydrogeology is quite closely working together with structural geologists because of the discontinuities, which are the faults in the subsurface. And what is very important is prediction and uncertainty. Prediction is always required from structural geologists if you want to drill a hole looking for oil, if you want to make another gallery in your mine looking for your ore body, you have to predict what is there. And you have cut it out, you have not yet drilled it. These operations can be very expensive. For example, today we have a visitor from ExxonMobil, and he just told me he made a structural geologic analysis of a place somewhere in the offshore, and he was able to convince his boss to drill a well which costs $100 million to look for a very, very large accumulation of oil, which could be extremely profitable. And the basis for this decision to invest $100 million was based on structural geology analysis. So it is all about a prediction. And maybe after the lecture you can ask me if he has found the oil or not. Predictions are always coupled to uncertainty. How sure are you that your prediction is right? This is, of course, important for predicting earthquakes. It's for predicting oil deposits or predicting a certain structure. It is never just a question, what is there, or what do you think is there, but how sure are you? What is the chance that it's not there? Okay? Prediction and uncertainty are very, very important aspects of structural geology. What are the methods that we are using? We are using remote sensing. That is becoming increasingly more important, and for all our students, life is now very easy with Google Earth sitting in your computer. You can see so much structures and tectonic features on our planet. Remote sensing is growing very, very rapidly, and it allows enormous amount of information to be processed and the understanding of structures in our planet. Lineaments, outcrops, all kinds of structures can now be mapped, and some of the satellite data which are available for us are really quite amazing. You have all used Google Earth to zoom in and see things which are only this big from outer space. One of our students is doing a mapping project to map over enormous areas small fractures in an outcrop phase using Google Earth data. Something which is also very, very exciting is the possibility to measure deformations from remote sensing data. You measure the altitude of a certain part of Earth, and then after some time you measure it again. And you will see that there are movements. Land is going up and down. Land is moving in different directions over a couple of years. Field work is essential. As a structural geologist, you have to get samples. Sometimes you work in the mountains, sometimes you work in the desert, sometimes you drill holes. What is very important is that we have to work with oriented samples. Structural geology is all about orientations. Where is the fault axis going? Where is the fracture going? So when you take a sample from the field, you have to make sure that you know how it was oriented. Interpreting seismic is another very, very important method that we use. We get data from the geophysicist of seismic reflection, and we can try to interpret the horizons, we can interpret the faults in these structures, use well logs, the measurements, geophysical measurements in wells, to tie them into the seismic data, analyze the cores, and in the end make a model of what is there in the subsurface. Of course, the analysis of morphology, of shapes, is very important. Structural geologists must know how to make profiles, and you have learned quite a lot of that in the Kartenkunde lectures. Geostatistics, mapping, are just tools that we are using all the time. And then, much smaller. Structural geologists take thin sections and use the microscope to deduce conditions in the past. We can work together with the petrologists, estimate strain measurements. Strain is something that I will talk about in the next lecture. Balancing palimpsestic reconstruction is a very important toolbox for structural geologists. What that is a technique to take a deformed rock and undeform it. So just imagine a car which has been in a crash. You use your computer to undeform it. It is a kind of playing back the movie of the deformation, palimpsestic reconstruction. And I will show you, of course, examples of all these techniques over the course. Numerical modeling and simulation is becoming very rapidly more and more important. For example, the research in our group is very strongly involved in numerical modeling. And then the last one is scaled physical modeling, making a sandbox to actually generate a small-scale model of the Earth. And this brings me to models. So what is a model? A model is some kind of a simplified representation of a phenomenon in nature. Models are always wrong. Models are simplified, and the outcomes of models are therefore never absolutely accurate. Some models are more accurate than others, of course, but you can say in general that a model is wrong. It's always wrong, but it can be very useful to help you with your scientific thinking to make predictions. Now, in structural geology and tectonics, there are three main classes of models. The first class is geometric models. A geometric model is a representation of a shape, of a geometry. So, most of you have been in the field already, and you have made a sketch in your field book of some kind of a structure. That is a model. You've actually made a very simple geometric model in 2 dimensions, probably, of some kind of a structure. Most of these models are qualitative, therefore they are not really accurate. But of course, if you want to find oil, you have to make your models highly quantitative and very accurate. And you have to quantify, you have to give numbers to how good the predictive capability of these models is. Modern geometric models, as they are used in the minerals industry or in water flow simulations or in oil and gas field exploration and production, are usually built upon a database. There are lots of informations of measurements in cores, in seismic, and maybe field. And these are all coupled in a database. And the result of this database